In this lesson, we study the emitter-bias configuration of an NPN transistor. Our goal is to connect the circuit equations with the physical feedback mechanism that improves DC stability. We will first form the DC equivalent circuit, then analyze the base emitter and collector emitter loops. After deriving the governing equations, we will calculate a complete operating point, examine how the emitter resistor reduces sensitivity to transistor gain, determine the saturation current and DC load line, and finish with a design example. Throughout the lesson, we use the constant base emitter voltage model with a silicon drop of 0.7 volts, and we assume active region operation unless saturation is being calculated. By the end of this lesson, you should be able to explain the negative feedback action created by the emitter resistor, derive the base current equation from the input loop, and obtain the collector emitter voltage from the output loop. You should also be able to calculate all important node voltages, check whether the transistor remains in the active region, and find the saturation endpoint of the DC load line. We will compare emitter bias with fixed bias so that the improvement in stability is quantitative rather than merely descriptive. Finally, you will use a target operating point to calculate transistor gain and select the required base resistor. The prerequisites are the basic NPN current relations, Kirchhoff's voltage law, Ohm's law, and the DC rule that coupling capacitors behave as open circuits. A fixed bias circuit can move substantially when temperature or transistor current gain changes. The emitter resistor adds a self-correcting action. Suppose collector current begins to increase. Emitter current also increases. So the voltage across the emitter resistor rises because the base supply must now overcome a larger emitter voltage. The effective voltage available to drive base current is reduced. Base current therefore decreases and opposes the original rise in collector current. This is negative feedback. It does not make the operating point completely independent of transistor gain, but it reduces sensitivity. The guiding question for the lesson is therefore causal. How does the emitter resistor translate a current change into a voltage change that acts back on the base loop? This is the complete common emitter amplifier. The input signal is coupled to the base through capacitor C1 and the output is coupled from the collector through capacitor C2. For DC analysis, both capacitors are open circuits, so the signal source and load are disconnected from the bias network. What remains is the supply VCC, the base resistor RB, the collector resistor RC, the transistor, and the emitter resistor RE. The emitter resistor is the key addition compared with simple fixed bias. It develops a DC voltage proportional to emitter current. That voltage participates in both the base loop and the collector emitter loop, so we must include it consistently in the equations. A reliable analysis becomes easier when we separate the circuit conceptually into two loops. The base emitter loop determines base current. Once base current is known, collector current follows from beta times base current and emitter current follows from beta plus 1 times base current. The collector emitter loop then determines the collector emitter voltage and the remaining node voltages. In both loops, follow the indicated clockwise direction. When we cross the supply from negative to positive, we record a voltage rise. When we traverse a resistor in the direction of current, we record a voltage drop. This consistent sign convention prevents the most common algebra errors and makes each term physically interpretable. After removing the coupling capacitors, since they offer infinite reactance at DC, the DC equivalent contains only the supply, the three resistive branches and the transistor. Notice that the base resistor is connected from VCC to the base, while the emitter resistor returns the emitter to ground. Current through the emitter resistor is the emitter current, not the base current. On the collector side, current through RC is the collector current. In active region analysis, emitter and collector currents are often close enough that the same current is used when deriving a simple load line equation. However, in the base loop, we retain the exact current relation IE equals beta plus 1 times IB. This distinction will appear explicitly in the next derivation. Apply Kirchhoff's voltage law clockwise around the base emitter loop. The supply VCC is a rise the voltage across the base resistor, the base emitter junction, and the emitter resistor are drops. This gives VCC minus IB minus VBE minus IERE equals 0. The transistor current relation is IE equals beta plus 1 times IB. Substitute that relation into the KVL equation, then collect the two terms containing IB. The result is IB multiplied by RB plus beta plus 1 times RE equals VCC minus VBE. Dividing by the effective resistance gives the base current equation shown in the result bar. The base current equation has an intuitive Ohm's law form. The available loop voltage is VCC minus VBE. The effective resistance is the physical base resistor plus a reflected emitter resistance. From the base, the emitter resistor appears multiplied by beta plus 1 because emitter current is beta plus 1 times base current. Therefore, a base current change produces a much larger emitter current change and a correspondingly larger voltage change across RE. We define the reflected resistance Ri as beta plus 1 times Re. When beta is large, beta plus 1 is sometimes approximated by beta, but the exact expression should be retained in formal work unless the approximation is stated and its effect is acceptable. Now consider the collector-emitter loop. Moving clockwise, the supply is a rise. The voltage drops occur across RC, across the transistor, from collector to emitter, and across RE. The exact KVL equation contains IC, RC, and IERE. For the usual load line approximation, emitter current is taken as nearly equal to collector current. We can then factor IC and write VCE equals VCC minus IC times the sum RC plus RE. The physical meaning is important. The supply voltage is shared among the collector resistor, the transistor, and the emitter resistor. Omitting Re predicts too much current at saturation and gives the wrong line slope. Once the currents are known, the node voltages follow directly. The emitter voltage is IE times Re. The collector voltage is the supply voltage minus the drop IC/RC. The base voltage is the emitter voltage plus the base emitter drop. The base to collector voltage is VB minus VC, and the collector emitter voltage is also VC minus VE. These relations provide useful cross checks because VCE can be calculated both from the output loop equation and from the node voltages. Finally, verify the operating region. For an NPN transistor in the active region, the collector base junction must be reverse biased with the stated sign convention. A negative VBC confirms this condition. In this example, the supply is 20 volts. The base resistor is 430 kilo ohms. The collector resistor is 2 kilo ohms and the emitter resistor is 1 kilo ohm. The transistor gain is 50 and the base emitter voltage is 0.7 volts. We will determine the base current first because it controls the remaining currents. Then we will calculate collector emitter voltage and each node voltage. The circuit image also shows coupling and bypass capacitors, but they are open for the DC calculation. Therefore, their values do not enter the bias equations. Before substituting numbers, keep the units compatible. Kilo ohms combined with volts will naturally produce milliampere scale current, while the base current is expected in microamperes. Substitute the given values into the base current equation. Beta plus 1 is 51. So the reflected emitter resistance is 51 kilo ohms. Adding this to the 430 kilo ohm base resistor gives a total effective resistance of 481 kilo ohms. The available loop voltage is 20 minus 0.7 or 19.3 volts. Therefore, base current is 40.1 microamperes. Collector current is beta times base current, giving approximately 2.01 milliamperes. The exact emitter current is beta plus 1 times base current, giving about 2.05 milliamperes. We will retain this distinction for the emitter voltage calculation, while the simplified output equation may use IE approximately equal to IC. Using the simplified output loop equation, VCE is 20 volts minus 2.01 milliamperes times 3 kilo ohms, giving approximately 13.97 volts. The collector voltage is 20 minus the drop across the 2 kilo ohm collector resistor, or 15.98 volts. Using the exact emitter current, the emitter voltage is about 2.05 volts and the base voltage is about 2.75 volts. Base to collector voltage is then 2.75 minus 15.98, which is negative 13.23 volts. This negative value confirms that the collector base junction is reverse biased. Small differences from a calculation that approximates IE by IC are expected and should be stated consistently. This comparison quantifies the improvement. When beta doubles from 50 to 100, the fixed bias collector current doubles from 2.35 to 4.71 milliamperes. Its collector emitter voltage falls sharply from 6.83 to 1.64 volts. With emitter bias, collector current rises from 2.01 to 3.63 milliamperes, an increase of about 81% rather than 100%. Collector emitter voltage falls by about 35% rather than about 76%. The emitter resistor therefore reduces gain sensitivity and preserves more useful voltage headroom. However, the operating point still changes, so emitter bias should be described as improved bias, not as gain independent bias. The stability mechanism can be remembered as a chain of cause and effect. If beta increases, collector current initially tends to rise. Emitter current follows, causing a larger voltage drop across the emitter resistor. The emitter voltage therefore rises. Since the base supply is fixed, the larger emitter voltage leaves less effective voltage to drive current through the base loop. Base current falls, reducing the collector current from the value it would otherwise reach. The loop acts automatically and continuously. This is DC emitter degeneration. If a bypass capacitor is connected across the emitter resistor, it may reduce AC degeneration at signal frequencies, but the capacitor remains open at DC, so the stabilizing bias effect of RE is retained. The DC load line is defined by the output loop equation. At the idealized saturation endpoint, collector emitter voltage is set to 0. The supply voltage is then dropped across the collector and emitter resistors. Because both resistors limit current, the saturation current is VCC divided by RC plus RE. For this example, 20 volts divided by 3 kilo ohms gives 6.67 milliamperes. The other endpoint occurs at cutoff, where collector current is 0 and collector emitter voltage equals the supply voltage, 20 volts. These two endpoints define the straight DC load line. The actual operating point lies on this line where the transistor characteristic corresponding to the base current intersects it. This graph combines the transistor output characteristics with the circuit constraint. The vertical intercept is the saturation current VCC divided by RC plus RE. The horizontal intercept is VCC. Joining these points gives the DC load line whose slope is -1 divided by the sum RC plus RE. Each blue curve corresponds to a different base current. The operating point or Q point is where the selected base current characteristic intersects the load line. A useful amplifier design normally places the Q point away from both cutoff and saturation so that the collector voltage can swing in both directions without clipping. The base bias network selects the characteristic while the output resistors and supply determine the load line. In the design example, the supply is 18 volts, the collector resistor is 2.2 kilo ohms and the emitter resistor is 1.1 kilo ohms. The target operating point is approximately 3.3 milliamperes at 7.5 volts with a base current of 15 microamperes. We must first determine the load line endpoints, then calculate the transistor gain implied by the target currents, and finally select the base resistor that produces the stated base current under the constant 0.7 volt base emitter model. This sequence separates the output constraint from the input bias design. After selecting a standard resistor value, a practical design must still be checked over transistor gain spread, resistor tolerance, supply variation and temperature. The saturation current is 18 volts divided by 3.3 kilo ohms or 5.45 milliamperes. Therefore, the load line endpoints are 0 volts and 5.45 milliamperes at saturation and 18 volts and 0 milliamperes at cutoff. The transistor gain required at the target point is collector current divided by base current 3.3 milliamperes divided by 15 microamperes, which equals 220. Rearranging the base current equation for RB gives VCC minus VBE divided by IB minus beta plus 1 times RE. Substitution gives approximately 910 kilo ohms, which is a suitable standard value for the stated model. 6 errors occur repeatedly. First, do not forget the emitter resistor in the output loop. Second, use beta plus 1 for the exact emitter to base current ratio and state any approximation. Third, do not interpret improved stability as complete independence from beta. Fourth, always check that the calculated voltages are consistent with active region operation, otherwise the model is invalid. Fifth, remember that 0.7 volts is a teaching approximation, not a universal constant. Sixth, distinguish DC bias stabilization from AC degeneration. A bypass capacitor can reduce the AC feedback while remaining open in the DC equivalent. In practical design, extend the nominal calculation to component tolerances, supply variation, temperature, power dissipation, and the required undistorted signal swing. Use these questions to test both conceptual understanding and calculation skill. Begin by explaining the feedback mechanism without equations. Then derive the base current equation from KVL and explain why the emitter resistance is reflected by beta plus 1. In the numerical exercise, calculate base current, collector current, emitter current, collector-emitter voltage and the node voltages. Next, determine the cutoff and saturation endpoints and verify that the calculated point lies in the active region. Finally, reverse the process. Use a required collector current to estimate base current, then rearrange the equation to select RB. For every numerical answer, state the device model and check whether the result remains physically consistent with the supply limits. The emitter bias configuration improves DC stability by converting a current change into an emitter voltage change that acts back on the base loop. In the base current equation, the emitter resistor appears multiplied by beta plus 1, so even a modest resistor can have a strong influence. On the output side, both the collector and emitter resistors contribute to the voltage drop, saturation current and DC load line slope. A complete analysis proceeds from base current to collector and emitter currents, then to collector emitter voltage and the individual node voltages. Finally, every result must be checked against the assumed operating region. The central sentence is this: increased emitter current raises emitter voltage, reduces effective base drive and opposes the original increase.